All right. What we did up until now, as far as noise is concerned, we looked at the physical phenomenon giving rise to noise. We saw that there are different mechanisms for generation of noise. And then we actually, based on those, we developed some models for the noise in transistors and diodes and active devices and passive devices. So we know now what the model for that is. So now we are going to go to the circuits. And we started talking briefly about an example. We did one common source, for example, and looked at it. But one of the key things to think about noise is that, generally speaking, if you think about it, each device, each transistor may have multiple noise sources, right? For example, if you look at the bipolar transistor, you have the shot noise of the collector, you have the shot noise of the base, you have the thermal noise of the base resistance and all the other resistances that you might have, you have flicker noise, you have all sorts of different things in there. Now, or in MOSFET, the same thing. You have the channel noise, you have the gate noise associated with the resistance, things of that sort. So you can imagine that you will be dealing with a bunch of different noise sources, right? So in general, if you have a large circuit, like some of the circuits we've talked about earlier, you will be dealing with a lot of resistors. So the question is that, is there a way to aggregate all of these things in one place? Is there a way to combine all of them into some sort of a noise? And we started talking about this, is that if you have, for example, an amplifier, you can think about putting the noise at the input of the amplifier. So one of the things we did, we said, okay, well, let's say this is your box, that has all of these noise sources inside. So you have all sorts of noise sources, current and voltage noise sources, et cetera, inside. And it has an input port and an output port. You can think about it as a two-port. We want to say, can we represent this with a noiseless amplifier or noiseless system in general, noiseless, let's say two-port, and put a noise source at the input? So can we aggregate it, for example, in one voltage source like that? And we tried to do that last time, so let's do another variation of that example. We can, for example, do a simple bipolar example. So let's do a BJT. And if you look at this, and let's say you have an R1 resistor R1, you have a V in and a V out. Let's ignore RO for now. If you don't want to ignore it, just assume it's part of R1. And what is the gain of this thing? We know it's GMR1, right? The voltage gain from the input to the output. So we know that already. And what are the noise sources, right? So let's just talk about a couple of noise sources to make things relatively straightforward, so we don't make our lives too complicated. And because we're trying to. So let's look at the collector shot noise for this discussion. And let's look at the thermal noise, Johnson noise of the R1. So we know this noise as a current source. This is what? 4kT over R. And we know this noise source, shot noise, collector shot noise, is going to be 2QIC. Right? So these are the two noise sources that are present there in the system. Now, we can say, okay, so and this gives rise to an output, actual noise in the output. So how does it give rise to output? Well, this is a current. It gets converted to a voltage. How does it get converted to a voltage? Through the resistance on that node. If you ignore RO, what is the total resistance on that node to ground? From that node to ground, it's simply just R1, exactly. So what is the total noise at the output? If I say VNO, V noise at the output squared over, so this is the noise power spectrum or our spectral density. So basically, it would be what? It would be the sum of, and these two noise sources are uncorrelated, right? Because they're generated by two different mechanisms in two different devices. There's no reason for them to be correlated. So you have to add them in power. You add the power of these noise sources. So basically, and then multiply it by R1 squared to produce the output voltage power. So basically, you have IR delta F, the noise of this resistor, plus the power of that, plus the shot noise, current shot noise power at the output, and then you can plug in values, so you get R1 squared, 4kT over R1 for that one, and then you get 2QIC, the DC bias, DC current in the transistor. So you get that, and then if you go and simplify it, you will get, well, let's keep it the way it is right now. It's okay. So that's that. You can multiply it out and get some numbers, right? So that's the noise at the output. This is real. This is something that you can go and measure. You have a sensitive measurement system, you have a sensitive spectrum analyzer, you have a good very low noise amplifier that you attach there and put it into a spectrum analyzer. This noise is present there. This the fluctuation of the voltage will have this kind of spectrum. Right? But now we say, okay, well, there are lots of noise. So that's where noise really matters. So this is the procedure. You have to think about where the noise actually shows up. But then you can say, well, what is my input referred noise? Meaning, what is the noise voltage noise source that I can put at the input that would produce the same effect at the output if I remove every noise source? If you can think about nulling the noise sources, but just, that's not really the right way of saying it, but if you just remove all the noise sources, set them to 0, right? So they will disappear. These are current sources, they will disappear. You can say, is there a voltage source, a single voltage source at the input that I can introduce that would produce the same exact output noise? And the way to do it is simple, because you know the transfer function from this point to that point, right? And we know how noise behaves with respect to transfer function. We've looked at LTI system. We know it's a transfer function magnitude squared. Right now, we are not dealing with frequency effects so far. So what's the transfer function? It's the DC gain. It's GM-R1. So you need to kind of divide it by GM-R1 squared, both of them squared, to get the effective input noise that would produce this kind of output. So if you take that and say, okay, well, then Vn input, the input, so this would be Vn out, equivalent over delta F is basically 1 over the transfer function magnitude squared. So in this case, it would be A of whatever, j omega magnitude squared times Vn out squared over delta F. And now, of course, in this case, this is simply GMRL, because right now we are looking at low frequency, so it becomes 1 over GM squared R1 squared times R1 squared. So now I'm plugging the terms in. 4kT over R1 plus 2QIC. And when you do that, you will see that obviously these two guys cancel each other, right? And then you're left with that GM thing. So you can actually rewrite this as 4kT over GM squared R1 plus 2QIC over GM squared. Now, we can actually manipulate and massage this a little bit. And we'll do that because there's another form that may also kind of be interesting to look at for this. Some people don't do that, but just like I think it's important. We'll do that in a second. But before we do that, let's talk about this. This is not real in the following sense, that if you take a noise meter or a spectrum analyzer and put it here, attach it here and try to measure this noise, very sensitive measurement device, you will not measure this quantity at the input. This is what you would have to put in there if everything else was noiseless to produce that output. It's a fictitious noise source, if you will. And I'm emphasizing this because it's important not to think in reality when you're experimentally working with this thing, this noise is not physically there. It's just the equivalent effect. It's something that would have captured the equivalent of everything that's in there. So the reference for your calculation of noise and measurements of noise is the output. Right? So when you do noise measurements, you have to really look at the output. But you can refer to the input, say, well, this is what the equivalent noise at the input would have to be to produce this thing. So now that we understand that, let's go to this. I'm going to massage this. So this term, so first of all, let's look at this and see what does it tell us. If you wanted to reduce this input referred noise. Now, why do we care about reducing the input referred noise? Because this is where your signal appears, right? So if you have a signal, for example, so this is signal, you can see that it would be compared directly adding to the noise in this form, right? And so they would be compared. So you're looking at the sum of these two. Now, if one, for example, if the noise were substantially larger than your signal, obviously, if you don't do anything special, your signal will get buried in the noise, right? So you will not see the signal clearly because it would be a small, let's say it's a sinusoid, right? It would be a small sinusoid added to a giant thing like that, giant noise. So if you add these two, you will see something that looks more like that than that. Right? And then recovering it would require certain other things to do. I mean, there are lots of tricks and techniques and things of that sort to reduce the effect of noise and recover it. There are some things that you can do to the signal. So there's also there's system design aspect to it, which is basically how you design your circuit to make this noise as low as possible. And then there's signal design. Right? These are two breakdowns of engineering thinking, at least electrical engineering thinking. Okay? Signal design is that how do I, if I know what I'm going to do with this, if I can make this signal in such a way, if I can design the shape of my waveform so that they become less sensitive to noise or other things. And generally speaking, a lot of courses talk more about system design than signal design. But signal design is probably as important as system design. So that's one way to think about it. Again, just like we're not getting into that depth. But so anyway, going back to this conversation, you see that this is useful because it allows you to compare it with a signal. So let's see. If I wanted to minimize my input referred noise, what do we need to do? Look at the parameters, right? So K we cannot change. Boltzmann factors. Temperature is whatever it is. Of course, I can say, well, of course, I can go to lower temperature. Yes, it helps you. And if you want to get really low noise stuff, I mean, really low noise stuff are really operating at really low temperatures. Cryogenics, right? Now, the other thing, the design parameter that's really kind of like at our disposal the most is GM, right? You can see that as you increase the transconductance, you're reducing your input referred noise. But if you look at the output noise, for example, right? If you try to reduce, for example, increase the transconductance, you're increasing IC. So your output noise is actually going up. And your input noise is going down as you increase IC, for example, let's say. So which one is important, the input noise or output noise? Which one? Should we increase the resistor current or reduce it? Because you see, the output noise is going up if I increase IC, and your input noise is going down because GM is IC over VT, right? So which one what should I do? Should I increase the current or should I decrease the current? Increase the current, right? Why? Because it's the input referred noise that gets compared. If I increase, the way it works is that yes, the output noise does increase if you increase the current, but so does your gain. And your signal gain, so the power of the signal is proportional to GMR squared. So you get more signal power increase than you get noise power increase, so your signal to noise ratio improves, and that's reflected directly in the input referred noise. Input referred noise is another way of thinking about signal to noise ratios. So I'm talking about this from different angles to make sure that it's very clear what we are trying to do. So, okay, so that's what it is. Now we can actually play with this a little bit in terms of the way it's written, because remember, this is thermal noise. This term, the first term, is due to the thermal noise of the resistor. This is due to shot noise of the collector current, right? But if you play with these quantities, and if you just plug in the value, the value of GM, how its GM is written, so we can write as 4kT over, now I take one of the GMs, I keep one of the GMs, GMR1, and then write the other one as RM. Okay? I just took one of the 1 over GMs, wrote it as RM. And then take the other one, I see 2QIC, and I take one of the GMs again to write as, what is GM? IC over VT, and VT is KT over Q, right? So I can put the Q here. And then there's another GM, and this is IC, right? So you can see that this cancels that, this cancels that. So what do you get? You get 4kT RM over GMR1 plus what? You get plus, and I can write this as RM2. So I can write this as, let's just write it as RM here. 4kT RM, and then I get 2 kT RM. That's it, 2 kT RM. Right? So remember, this is the thermal noise of the resistor. This is the shot noise of the transistor, collector shot noise. So I can factor the 4 kT Rm. And what I'm left with is, what we're left with is GMR1 plus 1 half. 1 over GMR1 plus 1 half, right? It's just manipulating the parameters, right? I mean, it's just basic algebra. But this way, you can actually see something else when you write it this way. So you can see what should dominate and when. Which term dominates? Is it the shot noise that dominates, or is it the thermal noise of the resistor that dominates? Now, if this amplifier is a decent, well, it's all of them are decent, but just if it's an amplifier with sufficient gain, right? If you have sufficient gain in this amplifier, let's say gain is significantly larger than 2, then what dominates? Shot noise dominates. If gain is very low, comparable to 2, then both of them matter. Right? And of course, if gain is significantly less than 2, then the thermal noise of the resistor matters, which makes sense. Because what happens is that essentially you have loss from here, so most of your noise is dominated by the resistor anyway. Right? And if the gain is, if the GM is high, if the gain is high, it means that yes, this guy generates whatever it wants to generate, but from an input perspective, you have so much gain for the signal that the signal is going to be significantly larger than that. So you're going to be dominated by this thing that scales the same way. So these are the facts. Now, it's interesting that you can write the shot noise this way when you refer to the input. Right? You can write as 2 kTRM. It's shot noise. But you have to remember, it's a different kind of noise. Even its distribution and power spectral density is not the same as a thermal noise. So this is just a low frequency component of it. So don't read too much into it. But it's interesting that you can do that. So is this good then? Are we all set in terms of, so we have defined this input referred voltage, right? But, and let's say if I had a voltage source the way I had shown it, so let's say you have an input voltage source connected here, it's all nice and good, right? Because it allows you to capture it. But what if I didn't have what if I didn't drive the input with a voltage source? What if I had driven it with a current source, for example? So let's say my input was a current source. So this is V in. This is the signal. Or I in. Actually, not V. I in. Right? So if I drive the input with a current source, and if I had that voltage source by itself, that orange voltage source, the input referred voltage source, what kind of noise would I get at the output? How much noise do I get at the output? Think about that. Well, if you're in doubt, use superposition from a linear perspective, a small signal perspective, right? When I null I in, what output would V in generate? Nothing, right? Because what happens is that when I null it, this disappears. So you have a voltage source that's open on one end. If you want to think about it, if that bothers you, think about a very large resistor on this side. So you have a voltage divider between a very large resistor and R pi. So most of your voltage will drop across the very large resistor. Now, if that very large resistor becomes infinity, then no voltage drop across R pi. Right? So what does that tell you? But does that mean that there's no noise at the output if I drive this with a current source? No. I mean, this resistor doesn't care, for example, right? Whether or not what you put at the input. It will generate its own noise. So will the shot noise of the collector. It would be the same. If you have a bias current, if you're maintaining a DC bias current, it would produce the noise there. So the output noise is there. But somehow our model has broken down because basically now this produces nothing. So this is an example to show you that this voltage noise is not sufficient to capture all the scenarios, right? Essentially, it only works when the source resistance is 0. So this model is incomplete. Now, what is the complete model? It's not far from that. You basically need 2 noise sources. You basically need a current source and a voltage source. And if you do that, you will see that actually this works out. The way to think about it, another way to think about it is that if you had another current source here too, so instead of this, you also had a current source. So you have the combination. So when it's, for example, when it's in the two ends of the spectrum, when it's open, this current source is producing some input noise at the input. So that's where the noise will appear. What generates the input noise, the noise at the input that would get to the output. And if it's short-circuited, it's this guy that's dominated. And if you have some other impedance, both of them will contribute, other than 0 and infinity, right? If the impedance is anything other than those. So in general, any two-port, any linear, LTI linear two-port, can be modeled with as many noise sources as you have. Can be modeled with two noise sources, an input-referred voltage source and an input-referred current source. Now, let's calculate what the input-referred current source has to be in this example, because we've calculated the input-referred voltage source. We need to also calculate the input-referred current source, right? What is that input-referred current source? It's something that needs to produce this output when, for example, when the input is open. When I keep the input open, it has to produce that output, right? So what do I get? What do we get if we, for example, have this current source? So let's say this is I in squared over delta F. What is the transfer function from this I in squared to the V out? Well, there are different ways to think about it. One way is that this hits R pi, becomes V in, and that V in goes through the gain. It's a little bit of a longer path, but let's do it that way. So we know that I in squared over delta F times R pi squared. So now this is the voltage that this induces here, the input. And this voltage goes through the voltage gain, which is Gm squared R1 squared, to produce the output voltage. So this is V out squared over delta F. Now we know what V out squared over delta F is, so from this we can calculate what I in has to be. So we say I in squared over delta F has to be 1 over R pi squared times 1 over Gm squared R1 squared times V out, which is that thing. R1 squared, 4kT over R1 plus 2QIC. And if you do that, you basically see that this guy cancels that guy. So you're left with 1 over R pi squared, 4kT Gm0 R1 plus 2QIC over Gm squared, which is essentially this thing, right? If you want to write it that way, you can write it as 1 over R pi squared, or in general, it could be Z pi, right? So I can actually write this as Z pi without loss of generality, but then if it's an impedance function of frequency, Z pi, Z pi, Z pi, and then for at low frequencies, then you get this being 1 over R pi squared, 4kT over, or we've already written that, times V in squared over delta F, the input referred noise. The N in, we called it. So this should be probably should call IN in. So you have the two noise sources, right? You have a current noise source, and a voltage source noises, right? What happens, so look at these two, and I have a question for you. Are these two noise sources correlated, partially correlated, uncorrelated in this example? What can you say about the correlation between these noise sources? Because it does matter, right? Because you need to take both of them into account. And the way you add the effect of them would depend on whether or not you assume that they're correlated or uncorrelated. So what do you think? Look at them and think about them. Think about where they're coming from.
Correlated because they're coming from the same source.
Yes, they're correlated because they're coming from the same source, right? It's the same exact source. I mean, even the expressions are the same, right? I mean, you can see. The same exact source. It's the random thermal movement of electrons here in the resistor, as well as the random passage time of the electrons through the collector-based junction that determine the induced noise in both cases. So when, for example, a bunch of electrons cross the, let's say, just there's a whole group of electrons that are kind of packed together and just cross the base collector junction, there would be a spike in both current and this voltage, right? So they would go up and down together. If you look at the random fluctuations of these things, if this is the current one and this is the voltage, they're going together completely, right? They're doing the same thing as they go. They're fully correlated, 100% correlated. Because they're caused by the same sources. This is an example of the same source. Because we are really kind of like, we need both of these things to take the effect of any arbitrary impedance at the input. But they are really capturing the same effect. And if you treat them like uncorrelated sources, then you won't get the correct results. Okay, so that's one example of how these things kind of work. And it's useful to think about it because it allows you to see what happens in a, let's say, in a standard system, and the fact that, but the good thing is that this is it. These two noise sources are it, right? You don't need to have anything else. You can capture, absorb everything. Now, are they always 100% correlated, these two? Do you think it will be always 100% correlated? Well, let's find out. Let's see. We'll run through some examples and we'll see what happens. So that's an interesting question, right? See, do they have to be 100% correlated all the time? Think about it. Okay, some of you are shaking your head. No, they don't have to be. And I'll show you an example where they're not 100% correlated. So in general, what you need to know is the value of more generally, power spectral density of this thing versus frequency, the power spectral density of this versus frequency, and their correlation factor versus frequency in general. And if you know that, you've basically completely characterized that two-port network from the noise perspective. And there are ways to measure these things. There are different things. There are different methods of measurements and actually measuring it. Because actually measurement of noise is a tricky proposition. Why do you think it's a tricky proposition? Yes? You might add your own noise. That's one reason it may be a tricky proposition. Yes, that's right. But why we are particularly prone to that when, as opposed to measuring the gain, is not as hard of an amplifier? Yes?
Because it will have really high frequency components, so if you have even a little bit of capacitance on your probe.
If you want to, for example, measure the frequency spectral density of this thing, you're right. I mean, so in the sense that if you look at the spectrum of this thing, you may say, well, if you're really interested in high frequency components of it, this can be affected by whatever you have. But I mean, what I'm asking is actually even simpler than what your answers are very good answers, but just saying that I'm asking something even more trivial. This noise is really small, right? So it can get buried in the noise of your measurement equipment. As you kind of pointed out, you add your own noise, but just like basically, so you have to use something, either a method, you have to have a method to measure the noise with something that's much lower noise than itself. But then the question becomes, okay, let's say the lowest noise system that you have, how do you measure it if you're measuring it without way? So you need to think about where you're measuring it, right? Sometimes, a lot of times, for example, you're measuring at the output where it's already amplified. So you want something that whose input referred noise is less than the output noise of this thing. So you may be able to compute that. So that's interesting. So there are like ways of getting to the lower and lower noise calculation. There are ways that make it a little bit independent of this thing, like there's two temperature measurements where you basically set the device, you have two different sources. Basically, it could be the same source at two different temperatures, or you emulate the effect of having a resistor at low temperature and having a resistor at high temperature. Sometimes actually you actually physically do that. You cool something down and then measure it, and then you kind of heat it and you measure it again as a noise source. And since the temperature is a measurable quantity, and Johnson noise has a direct relationship, it's a thermodynamics thing. related to that. So you know what your noise is, and then you do 2 measurements with a known noise source at the input, and you measure the excess noise at the output. It's called a Y factor measurement. And from those 2 measurements, you get 2 equations and 2 unknowns, and you solve them. It's called Y factor. Now, but the other interesting thing is that now, so that's one kind of noise, and noise kind of shows up in all sorts of places. We may even get a chance to talk about this a little bit later. There are other devices, like an oscillator, right? His noise will enter the system, and it will affect its performance. Sometimes it shows up as what we call phase noise and things of that sort, right? It changes its phase fluctuations and all those things. So let's say you have a device, an oscillator, for example, that is very low noise. When you're measuring the phase noise, you're measuring timing accuracy, right? How do you quantify timing accuracy? How do you need to have a time reference to quantify how much you're deviating from an ideal time reference, right? So you need a better time reference for that. And to measure that, you need to get a better time, right? How do you measure your best time reference? How do you quantify it? How do you know that that's the best time reference? Have you thought about this?
Make 2 of them and see how far they desynchronize?
Okay, two identical ones, right? So if you have 2 identical ones, if you can make 2 identical ones, and if you're making an assumption, that's correct, what you said, that's very interesting. So you don't need 1. If you have 2, then you can look at the deviation of the 2 with respect to each other, and there's a square root of 2 because you're kind of adding them independently and all those things there, but there's a correction factor. But what if you could not guarantee that they were identical? They have identical properties. Can you tell? So let's say you are on a deserted island and you have 2, this is a little bit of a side note, but it's kind of like the measurement of noise is actually interesting. So let's say you have 2 time reference sources, and can you tell which one is better? You may say, well, I can tell if I give you something like this, like let's say, well, these are the time references. So let's say I go like this. So this is the first one, and this is the second one. Right? So which one is better? Second one. First one. Okay. Okay. But how do you know? How did you know? Yes. So you use the 3rd time reference, your own time reference, right? Which in this example may work because it was so blatant compared to your time reference that you could tell. But if you have 2 atomic clocks, for example, it may not be as straightforward to do that, right? So what if you have 2 time references and you don't know if they are equal? You can measure the relative deviation of the relative deviation. Can you tell which one is better if that was all you had? You can't. Like in this case, you use the 3rd time reference, which was you, right? You can't. But the interesting thing is that now if you have 3 time references, you actually can. Because you can measure them like you have 3 two-way combinations. And you get 3 equations and 3 unknowns. And you can solve those. It's kind of interesting. Anyway, so a lot of these things sometimes kind of like boils down to these like 3 measurements and all those things. Direct noise of the devices may not directly do that, but there are other scenarios where these kind of things can actually pop up. So this is quite interesting to think about. How would you measure these things that are at the limit of performance? But that's not the primary subject of this course.